All right. Well, happy holidays, Merry Christmas, and all that stuff. Chapter 16, day 1. Chapter 16, we did some in class. That was the pretzel problem, the candy bar problem. For those of you that played roulette, that's what we're going to be talking about in Chapter 16. We first start out Chapter 16 with some definitions. And the first definition is random variable. And so if we think about those two words, variable, it's a value that can take on a variety of meaning. And random, we're not sure what's going to happen. And so random variable is defined to be the value of an event, a random event, denoted usually by a capital letter. So random variables is the value of some event. And we use capital letter X or capital letter Y or Z are probably the three most common that we use to represent that random variable. And we'll talk more about random variables as we move through the chapter here. We have a couple types. The first type of random variable we're going to talk about is what we call a discrete random variable. It has a finite outcome and is countable. So a discrete random variable would be counting maybe how many people are in your family. 1, 2, 3, 4. Those are discrete numbers. Another type of random variable that we have is a continuous random variable. So we think of more of it being on a continuum, a number line that has infinite number of possibilities in it. And so a continuous random variable is an outcome which can be any number, including decimals. And I think more of this when I think of like how fast someone could run a mile. Depending on how many decimals I want to go out, I can really have a unlimited amount of answers. And that's on a continuum. If I ask how many miles did you run, 1, 2, or 3, that's discrete. How long it took you to run would be more of a continuous. We are going to take a look at a problem that we did in class involving the pretzels, the chocolate-covered pretzels. And each class used different dice and different items, so I'm going to just do let's suppose we did the pretzel problem right now, in which I had a 10-sided die. So I have a dice with 10 sides on it, and I'm going to define you winning to be if you get 1 or 2, then you win. If the number 3 through 10 comes up, then I win. And if you remember how we played, you pay $1, get a pretzel. If you win, you get your $1 back. Life was good. If not, you bought a pretzel, same as anything you would normally buy. So what we're going to do is when we have situations like that, we're going to make what we call a probability model. And this table that we're going to make is another name for a probability model. So if I ever say make a probability model, this is what I'm talking about. I'm talking about making a table. And the table that we make has some columns. First column is what's my outcome? What are the outcomes that I could have? All the outcomes. And I need to list all of them because all the probabilities then should add up to 1 when we're done. In the second column, anytime you're dealing with money, the easiest way to think of it is how much are you paying out? Don't worry about profit and anything like that. Just ask yourself, how much are you paying out if that person or thing or whatever wins the winning outcome? We have a column for the probability that we're going to pay out. Now again, our random variable is X. We're going to let letter X be the random variable, that variable being how much we're paying out. The probability that we make a certain payout is this column. And the last column, we're going to take the product of X, the payout, times the probability that it would happen. So let's think about the pretzel problem. 1 and 2, you win. If you win, the payout to you was $1. If you lost, you got a 3 to 10, which was a lose, the payout to you was nothing. You still got the pretzel, which was good, but if we think about this from a payout standpoint, either you paid out, I paid out to you $1 or nothing. Now, the probability of you winning was 0.2. If we did a 10-sided die and you won on the numbers 1 and 2. I think we did maybe 50% in class or 60% in class, but all classes were different. So I'm just going to choose 1, 2, you win. 3 to 10, I win. Whoops. Happens. The probability that you get 3 through 10 then was 0.8. And so I'm just filling in a table. All right? Next, I can take the x times the p of x. So 1 times 0.2 is 0.2. 0 times 0.8 is 0.8. And we're going to have a use for that here in just a minute. So we can take any situation that we have and we can make a probability model, which is this table, of that situation. Now, for those we talked about, if I made a sign, remember in class I said, hey, if I made a sign and I said all pretzels are a certain price, what I'm really doing is I'm calculating what we expect the pretzels to be in the long run after the law of large numbers come into play. And what that value is called the expected value. So from that table, we can calculate what is called an expected value. And the expected value is the mean of a random variable. And another word for mean is average. The mean or average of a random variable is called the expected value. We use symbols. These are the symbols we use. And I know my handwriting is terrible, but a symbol you might see is capital E of the x, or mu of x, okay? That is the expected value. The formula for expected value is as follows. We're going to take, whether I write it this way or this way, we're going to take each of the x times p of x. Sub 1 means the first one. This would be x sub 1 times p of x sub 1, the first piece, plus the next one, which is this one, plus all the way until you're done with all of your table. So this formula says, let's take each of these products and add them together. Whatever that sum is, that's expected value. So for our pretzel activity, we had, let's go back up, 0.2 plus 0.8. So I'm sorry. Do you notice my math mistake here? 0 times 0.8 is 0. I know what you're thinking the whole time. Mr. Pat, it's 0. Yep. Okay. 0.2 plus 0. 0 times 0.8 is 0. So 0.2 plus 0 is 0.2. That's the expected value for the pretzel problem. So the expected payout is, in money, 20 cents is my expected payout. So when we do the table, we always think of this as our payout and what we expect to pay out. Now, one question that we could always ask is, well, what's my profit? Well, in this case, my profit would be $1 to play, right? Minus the 20 cents that I'm paying out. So I take $1 in, I pay out 20 cents. My expected profit is 80 cents then for every pretzel. So my sign would say all pretzels 80 cents instead of all pretzels $1. Now, if my expected payout was $1, okay, and it was $1 to play and I'm handing back $1, there would be no profit. I would also not have any money to pay for the pretzels, but if it was, let's say no pretzel was involved. If the payout and the cost are equal, that's a fair game. Okay? I know it seems kind of silly, but think about it. If I had a coin, and I don't know if I have a coin, I do. Let's play a game. You give me $1. I'm going to flip the coin. If I get a head or a tail, I will give you back your $1. Oh, look, tail. Here's your $1 back. Play again. You give me $1. Tails. You get your $1 back. That's a fair game. You gave me $1, and the chance that you won, the expected amount that you won is $1. So therefore, it's a fair game. Fair game is this. The cost to play must equal the payout back. If so, that's a fair game. And you might say, well, wait a minute, Mr. Pat, it's kind of stupid. If heads I win and tails I win, why would I even play? I'd make $1 all the time. So let me change the game. Pay $2. Win on heads. Okay? So if we paid $2 and we win on heads only, let's see. Outcome. Well, you could get heads or you could get tails. I pay out, you're going to pay $2 to play. Okay? Now, I'm willing to pay out $1 on heads. So, if you get a head, I'll give you $1. And if you get tails, you get nothing. The probability of getting a head is 0.5 and tail is 0.5. So if I do x times p of x, 1 times 0.5 is 0.5, 0 times 0.5, okay? Add these up, my expected payout is 50 cents. Is that a fair game? Pay $2 to play, win $1 on heads. Nope. But what if I charged you 50 cents to play? Okay? I'll keep this back here for a second. Let's make a new table. All right? One more. Pay 50 cents to play. Pay out $1 on heads. So let's try this one. Again, outcome. I get heads or tails. This is my payout. I'm going to pay out $1 if you get a head. And I'm going to give you nothing if you get tails. The probability that you get a head is 0.5. The probability you get a tail is 0.5. Okay, same probabilities as before, but now x times p of x is 0.5 and 0. I add them up because expected value is the sum. So I expect to pay out 50 cents every play. Even though I'm paying out $1 on heads, I pay nothing on tails. Is this a fair game? Well, the cost to play, 50 cents. The expected payout, 50 cents. This is a fair game. And when we develop our own games for our projects, you're going to have to develop a fair game. And we'll talk about that later. Okay? But fair games, this one's not fair. The cost to play must equal the payout. We talked about a game in class called roulette. That's in the casinos. And so what I want to do is I want to look at what is the expectation. That's another word for expected value. It means the same thing. Okay? Expected value. It's another word for expected value. What is the expectation if you play a single number on a roulette wheel? Now, we have to make some assumptions. We're going to assume that we're having just a $1 bet. And for a $1 bet on a number, you win $35 plus the dollar that you bet. Okay? So assume a dollar bet, and for a dollar bet on a number that you pick, you will win 35 plus the dollar that you put on the table, you will get back. All right? The roulette wheel, we took a look at roulette. All right, here's our roulette wheels. They have numbers 1 through 36, 0 and 00. There's 38 numbers. What are the outcomes? Well, you might win. In other words, your number got picked, right? Now, the payout, because you're going to get $35 plus your dollar on the table, you actually take in 36. Because you give your dollar to play, they give you back 36. Don't worry about profit yet. If you lose, you get nothing and like it. That's the way it goes. The probability you're a winner is 1 out of 38, because remember, there's 36 numbers plus 0 and 00. The probability that you're a non-winner, 37 out of 38. So it's just, you have to be able to calculate probabilities of situations to fill in this table, okay? Now, x times p of x, 36 divided by 38 is about 0.947, or if I round it, 0.95. 0 times anything is 0. So to calculate expectation, we take these two numbers and add them together. So, on average, the casino expects to pay back 95 cents to the hands of the players when they play. So if they expect to pay out 95 cents and it costs $1 to play, the casino makes 5 cents from every coin, from every person, on every spin. And you might say, well, how do they stay alive? Lots of spins. Okay? Last one to look at. This one actually comes from your textbook. And it's an insurance policy problem, talking about insurance again. Okay? That's an R right there. So insurance policy. And we talked about car insurance and life insurance. This one deals with life insurance. All right? Out of every 1,000 people, on average, one will die every year. Out of every 1,000, 1 out of 1,000 will die, and 2 will become disabled. Again, in this every year. Okay? So, out of 1,000 people, 1 will perish, and 2 will become disabled and not be able to work every year. Now, again, this is out of your book, so you can look it up in chapter 16. Assuming a death benefit of 10 grand per person and a disability payment of 5,000 per person, that would be for the year. Let's create our table and find the expectation of this insurance company. So here we go. Outcome. A person might pass away, a person might become disabled, or none. Nothing happens to them. They're living. This again is the payout to the person. The random variable is how much we're paying them. We're going to pay them 10 grand if they pass away. They don't get it, their family does. Pay them $5,000 if they become disabled, one-time payment. And they get nothing if nothing's wrong with them. Well, the insurance company is relying on some probabilities. And again, statistics show about 1 in 1,000 will pass away, 2 in 1,000 will become disabled, and the rest, 997 out of 1,000, have nothing happen to them. If we follow the rest of the table, x times p of x, 10,000 divided by 1,000 is 10. Disabled, 5,000 times 2 divided by 1,000 is 10, and 0 times anything is 0.